Okay, we're going to look at the last section here, which is section 6.3. It's called measures of position. Okay, so we've already looked at where the center of a bunch of data is, and we've looked at the spread or the variation of the data. And today we're going to look at measures of position. Now, position sort of talks about where you are, right? That's your position. So we're going to look at two things in this section. The first thing we're going to look at are what we call z-scores. Right? Z-scores are going to tell us where we stand relative to everybody else. And then we're going to look at box plots. And box plots are going to be another visual representation that shows sort of how spread out the data is in a different way than the bar graphs and histograms we've done before. Okay, so we're going to start down here looking at college entrance exams just as an example. Again, this is something that you would learn quite a bit about if you took a statistics course, which I think many of you may do. But the idea here is we have two different tests that are used for college admission. One of them is the SAT test, and one of them is the ACT test. Now, SAT scores, if you look at this first paragraph, have a mean score of 1,060 points. They have a standard deviation of 210 points. So how we would get that, right? We would take every SAT score, put them into a database, average them all up, and then use that standard deviation formula or some software to do it and figure out the standard deviation. Okay. Now, what we learned last class was that 95% of all scores should be within two standard deviations. So if we went up 210 and went down 210 and went up another 210 and down at 210, we'd have this sort of range, right? So SAT scores have a mean of 1,060 points. On the other hand, ACT scores have a mean of 18 points with a standard deviation of 6 points. Okay. Now, this sentence down here, right, 1,000 is a lot bigger than 19. But 1,000 on the SATs wouldn't really be considered a better score than 19 on the ACTs, would it? And now the question is, why is that the case? Okay, so we're looking at SAT scores where the average is 1,060 and the standard deviation is 210 versus ACT scores, right, where the average is 18, right? Something like 1,000 is a lot bigger than 19, right? But that doesn't mean it's a better score. We're going to have to look at a measurement of position. We're going to have to talk about where does the 1,000 put you in relation to the other SAT scores versus where does the 19 put you in relation to the ACT scores. Okay. Now, it turns out that the 1,000, right, is below average for an SAT score. Right? The average is 1,060. So if somebody scored 1,000 on the SATs, it's a good score, but it's a little bit below the average. On the other hand, this 18 points, or 19, sorry, that we're talking about on the ACT, 19 is considered above average. For the ACT score. Okay. And this becomes a big concept in both statistics and also just in everyday life to think about one thing we've always talked about, comparing apples to apples and oranges to oranges. You can't just say 1,000 is bigger than 19, so 1,000 is better. You have to look at where you stand relative to the rest of the population. Okay, so z-scores are going to turn out to be a numerical measurement of where you stand, whether you're above average or below average, and also how much above average or how much below average you are. And then it makes sense to compare things, right? We would not expect the rent of an apartment in Baltimore to be more expensive than the rent of an apartment in New York or Washington, D.C., where rents are higher. But you could talk about rent, how expensive is a specific apartment in Baltimore compared to Baltimore apartments versus how expensive a specific New York apartment would be compared to New York apartments. Okay, so it's all about relative comparisons, and that's where we're going to look at positions. Okay, so there's a formula here It's not a very complicated formula. We're going to talk about what we call the z-score, right? And here's our formula, okay? Now, it's got some symbols in it. Okay? We've talked about this x bar before, right, which is the mean. And I think an easier way to think about this formula rather than symbols is to think of it in terms of words. It's the data value itself. So the x is the value in question that you're trying to find the position of, right, minus the mean over the standard deviation. Okay, so the x bar symbol that you see over here, that represents the mean. The s you see over here represents the standard deviation. The x is actually the value in question that you're trying to find the position of. So I think rather than worry about a formula with symbols over here, it might be better to think of the z-score in this more informal but more helpful form. Take the data in question, subtract the mean, and then divide by the standard deviation, right? So if you think about it, when you do the data minus the mean, you're figuring out how far above or below the average you are. And then when you divide by the standard deviation, what you're doing is you're putting it relative to the spread. How many steps above average are you? How many steps below average are you? Okay? So the first thing we're going to do here is see how we would do a couple simple z-score calculations. It's a very simple calculation, but you do have to remember when you put it in a calculator to think about finishing the whole numerator before you divide. Otherwise, the order of operations might do something other than you intended. Okay, so we're going to look at this example down here. Suppose the average number of credits for a student at a college is 10 credits with a standard deviation of 4 credits. Now you're asked to find the corresponding z-score for each of the following. So in part A, we're looking at a student that takes 8 credits. That student is below average, right? They're taking less than the typical student. And again, we're not making any kind of judgments. We're not saying better or worse. We're just observing that it's below the average. And there's lots of reasons some people take less and some people take more. Sorry. The question here is to find the z-score for 8 credits. So in this case, this is our data value that we're trying to put and determine a position relative to the mean. So the mean is 10. Right? The standard deviation is 4. So the z-score for this student who takes 8 credits is going to be the 8 credits they're taking minus, right, the average 10 credits, that's the mean, divided by the standard deviation. Okay, so we just get our calculator out and do this calculation. Okay, now if you want to do it in your calculator, then you really need to think about in one step putting parentheses. Otherwise, you do 8 minus 10, which is negative 2, and then divide by 4, and that turns into negative 0.5. Okay, now it's true that you could call that negative 1/2. But z-scores are generally done in decimal form, and that's because the types of things you do with z-scores in statistics will end up using decimal values. Okay, so how do we interpret this z-score? Well, the negative sign here tells us that we're below average, and the 0.5 tells us how far below average we are relative to the standard deviation. So this is about a half a step below average, right? So, not significantly below average, but about a half a step below average. Okay, so that's what the z-score means. Right now, I just want you to focus on being able to do the calculation, and then we'll spend a little more time in the next section or the next example trying to make sense of the z-scores and how we could use them to compare things. Okay, so part B, same basic idea. This is our new data value, 15. We're going to take our z-score, right? I'll just scroll up a little bit so you can still see the formula. It says take the data minus the mean over the standard deviation. So our z-score is going to be the new data point, 15, which is above average, minus the mean over the standard deviation. Okay, now this is going to be 5 over 4, which again, I know the whole semester we've said leave things as fractions, but this is a case where we want to convert, into a decimal, 1.25. Now this is a positive z-score. That means it's above average, and it's more than a whole step above average. I still think the easiest way to think about steps and standard deviations and everything is to think about grades. If you think about a 70 being a C and a standard deviation of 10, you would have to be a full step better than a 70 to get into the 80s or the B category. Right? So a half a step is good, but you're still within that range. Once you get a z-score of 1, you're in that next sort of group, and that's, you can think about that bell curve we did a little bit with last time too. Okay, so some of the homework you'll be seeing and some of the calculations you'd have to do on a quiz would be just calculating some z-scores. Okay, whether you prefer to have a slightly shorter formula like the one here that has the symbols in it, or if you prefer it written out, which I think probably makes more sense, data minus the mean over the standard deviation. Okay, so this is z-scores. Now, how we can use z-scores then is to compare two scores. So let's do a little bit more formal analysis of what we did last time. We saw an SAT score of 1,060 with a standard deviation 210. We saw ACT scores had an average of 18 with a standard deviation of 6. So if we wanted to compare these two, the result of 1,000 on the SATs versus the result of 19 on the ACTs, what we could do is figure out a z-score for them, right? So we would do 1,000 minus 1,060. Make sure these look like zeros here. All over 210. Okay? And this one, the z-score, we're going to have to do 19 minus 18 all over 6. Okay? Now these don't turn out to be such nice decimals. Right? We're going to get a little bit more involved in our decimal. This is going to be negative 60 over 210. Right? And then we would get our calculator out and figure that out. This turns into, as a decimal, if you round to 2 decimal places, which is usually what we do for z-scores, negative 0.29. So a little bit below average. When we look at the z-score for the ACT of score of 19, we would get 1 over 6, which if we convert to a decimal, and I should probably use little wavy equal signs here to show that this is approximate, that would be approximately 0.16, a little bit above average. Okay, so when you want to compare two things, either on different scales, like SAT scores being in the thousands and ACT scores being tens, if you wanted to compare salaries 100 years ago versus salaries today, which are on different scales, if you wanted to compare heights of men and heights of women, you would do everything relative to the mean and the standard deviation. And, the higher the z-score, the further above average. The lower the z-score is a negative, the further below average. The closer to 0 the z-score, the closer to average. So I think if you wanted to compare two different things from different populations, you would just do these z-scores and then understand what the z-score means. Right? So let me just say it one more time while we're here. This z-score of negative 0.29 means that you are a little bit, 0.29, a quarter of a step or so below average. This z-score of 0.16 means you're a little bit above average. Now, if you had two z-scores that were both positive, the higher one would be the one further from the center, right? Which could be better or worse, right? A score on a test, usually the higher score wins, but cholesterol levels, right? You don't want to brag about necessarily having the highest cholesterol levels. So sometimes you want to be closer to the average. Sometimes you want to be more exceptional or further away from the average. So you really have to do your calculations and then think about which one would be considered better in the context of the question. Okay, so the first part of the section will be z-scores. Make sure you try a couple of these problems, and then the next video will have box plots, which is a separate idea. I just wanted to break them into two videos so it's not quite so long.